Hi, everyone. Vidhya is a staff software engineer at Netflix, and I'm going to turn it over to her.
Thank you, Amanda. Hi, I'm going to talk to you today about scaling key value store, some adaptive strategies for diverse access needs at any scale. You can notice the any is in italicized. When you go through my talk, you'll understand why. I'm Vidhya Arvind, staff software engineer at Netflix, data platform at Netflix, and a founding member of Data Abstractions. How to efficiently scale for any scale? When I say any, this is what I mean, where Netflix is streaming all over the world. All the reds you see in this map is where Netflix is streaming. Can we scale to all our data needs? Is the question. And when your use cases look something like this, where key value, time series, file system, relational, bobs, analytics, and queues are some of the use cases. And actual use cases are an intersection of these as well. Specifically, a key value use case can be a relational store or a blob store. A time series can be a queue or can be used as for analytics and searching. When your use cases are everywhere, and Netflix has use cases everywhere outside of these patterns, and as well as sometimes Netflix doesn't have any solutions for some use cases, that's possible. Can you take these common patterns and provide a common solution is the question. Can these solutions be generic and storage agnostic? Solution is data abstraction layers. What do I mean by that? I can go through in detail about what data abstraction is. Before that, I will be uh, using these three techniques that make it very valuable, right? Adapt to latencies, adapting to use cases, and adapting to growth. First, adapting to latencies. When your use case starts with 1 GB or few GBs of storage and grows over time to petabytes of storage, or traffic grows from 1 RPS, 10K RPS to a million and billions of RPSs, then what happens, right? We need solutions. And those solutions can be in the form of databases or caches. In this case, when latencies are hitting the database, when traffic is hitting the database, it will be latencies of hundreds of milliseconds. When it hits a cache, it's in microseconds, hundreds of microseconds. But when your cache is in your box itself, which in this case it's a near cache, your latencies are tens of microseconds, right? And with that also you can support more traffic increases, increasing from 10 million qps to a billion qps even when it's near cache. How to make the client adapt to these changes is the question. Especially when your clients are connecting to different data stores, and these data stores are varying. It has its own language, it has different language and rough edges, it has different tuning parameters, and cost models are so different, right, for each of these databases. How to make it more resilient? That's when data abstraction comes, and data abstraction sits in between your client and your storage engine. And it has a control plane component where control plane tells or dictates to the data gateway or abstraction layer what storage engine to connect to. Client is agnostic of what storage engine it's connecting to. Some of the adaptability techniques are how to make client adapt to changes using signaling. The signaling is like when the client connects to the server, it handshakes, and using the handshake we pass in some signals to the client how to tune itself for the data. And you keep sitting there and asking for more signals from the server, right? Signals can change over time, and that's why you need new signals to propagate to the client every time. Signals look something like this. The API is a handshake API. When you call for a specific shard, it returns a signal. Signal itself can pass in information like, oh, the client needs to chunk the data, and the chunking has to happen after 1 megabyte, and the chunk size has to be 65 kilobytes. And you can also pass in statistic information like I have 39 million documents that are being stored in the store, right? You can even pass information like compression. In this case, I'm saying the algorithm the client should use is an LZ4 compression algorithm. We can pass in signals like SLO. If I hit 10 millisecond SLO retry, or when the concurrency limit reaches 1,000, you can start shredding the load. Things like that should be passed in as signals. How to efficiently read data can we adapt for large data fetches is another question for adaptability. One way of adapting to large data fetches is using pagination. So when we talk about storage, we talk about storage being in SQL format or some query language that you talk about to the data store. In the client side, you talk through APIs, and the APIs looks like get, puts, deletes kind of APIs. And in between, the server should accumulate a page of data from the data store and send that page of data to the client. If I retrieve a lot more data than the client can handle, it's not. You're doing too many round trips to the database, and that's not efficient. Server talks to client using bytes, and that's exactly what you have to limit the storage engine by. You tweak the fetch sizes in the database so that you're only collecting as much as I can fill a page. You don't collect a lot of data and throw it away. That's a waste of resources. When you return the page to the client, you include a page token, and the page token will let you come back again to fetch more data for that particular partition. When you return the data, it's possible that you're sitting and reading so much data within for filling up a page that the client has already given up. For example, if there's data in the data store, but it's not reachable quicker enough, you're sitting there and retrying or getting the data again and again until you fill a 4 MB of page. The client has already given up. That's when SLO comes in. As soon as the SLO is reached or it's 80%, you return whatever you have. You might have only one item, or you can have several items. You can return whatever you have and come back for more data the next time. That way, you're not breaching the SLO. Can we adopt to linearizable latencies when the data is small or large, right? When the data is small, you need to return the data quicker. When the data is large, as the data size grows, you can linearize the latencies. Let's look at how small data are stored. Key value API, you can think of it as a 2-level hash map, right? It's a string and a list of items. You can also think about in the client side as a string of IDs and a sorted map or a tree map, right? When that's your data model, for simple cases, you can create this kind of store. Netflix widely uses Cassandra as a data store, and the DDL looks something like this, where ID is your partition key, and key itself is your clustering column, and value metadata, you have two more columns. Value is where your data is stored, and value metadata is an extra information about how to decode the value itself. So that's the DDL. And can we adapt to linearizing large payloads, right? Like when you store the data small, immediately stores into the value column. When it's large, you need to chunk the data. How do you chunk the data, right? You take a large payload and chunk it up into 64 kilobyte chunks, and you stream the chunks to the server. After the chunks are all streamed, you create chunk 0, which has information about the offsets and where the chunks are stored and information like that. And that is your commit, and you store the commit into the server. While reading, you read the commit 0 first, get the value metadata, and in value metadata, you have information about where to go fetch the data. So value metadata, when it's chunked, we can't store it in the same table. We have to store it in a different table. In this case, we are storing it in the data table. How we are spreading the load is by bucketing, because each chunk is 64 kilobytes, and we want to spread the load of megabytes of data into different nodes. That's using bucketing, and you can see the bucket number, and the key and chunk and version are the ID and bucket number becomes a partition key, and key, chunk, and version becomes the clustering column, and chunk itself is a value, and value metadata is stored. You can see that for each chunk here, each key is stored in different buckets. And chunk value metadata has information about chunk offset, XX hash of where to go find the key, and a version. It's illustrated here. You take key A with ID 1, and which has 1 MB of data. It's spread into 16 chunks, and it is spread it to 3 buckets, right? You take a 2 MB chunk, and when you XX hash the ID or the key, it'll land up in another set of buckets. The bucket here is 2 to 6, and the chunk is 1 to 32. Same with when the chunk become larger, you spread the load into different buckets and different chunks. It can be said that the key C here, 1 to 8 chunk is stored in first few buckets or first few nodes. In Cassandra, 9 to 16 is stored in different Cassandra nodes, and the rest is spread across the cluster. That way, you're spreading the load, and there is no one hot node. Version is used, so I illustrated how the chunk 0 is the commit chunk. When the chunk 0 comes in, it's stored in the base table here, but it's pointing to a version in different tables. The version 1 was sitting in a different bucket, and version 2, which is the latest version, sits in a different bucket here, 3400. So chunk or the value metadata shows where the chunks are stored. So that is adapting to latencies, right? Small payload, faster retrieval, large payload. It takes a village to get all the data. But when the use cases, how do you adapt to use cases is the next question. Especially when your use case is simple, you can say, I have a proxy and a key value store, and everything is stored just like that. But when say, for example, you have a tree use case, you want to represent your data as a tree, nodes and edges and data and leaf nodes. When it's very hierarchical data, you can have a tree abstraction in front and key value store next. Same with UI personalization, where you have a facade in front. It can be more complicated. This is our document store, where we have control plane, journaling, storage. It is using a bunch of technologies underneath. You have a search using Elasticsearch. You have quick retrieval using key value. You have journaling and auditing for the data as well. When you have shadow writes, when you want to move from one data store to another data store without user getting affected, you can do shadow writes as well. A namespace is a configuration that we use to show the how abstraction can be storage agnostic. Namespace is a virtual concept. It stores physical storage. Physical storage represents where the data is actually stored. You can add a cache on top. Here I'm representing namespace 1 and 2. One is pointing to Cassandra, another is pointing to DynamoDB. Depending on what namespace the request comes with, it will pass the data to that particular data store. Underneath, I have different data stores for each of these different storage engines. Cassandra points to Cassandra data store, and DynamoDB points to DynamoDB data stores. When the put call comes in with the namespace request, which points to DynamoDB, the request is forwarded there. Adapting for growth. When your use case is small, you picked a specific data store, but when the use case grows from GBs to terabytes, you want to pick a different data store. What happens when your data is already living in one data store and you want to move to another data store? More of these use cases happen in Netflix, where you're moving some of the data from key value, and it quickly becomes a blob store when you store a large amount of JSON or proto files. When that happens, we want to do migration. Migration happens by wiring a primary store and a secondary store. All the writes and reads go to primary as well as secondary. And we are using the namespace configuration to specify which is the primary store and what is the secondary store. And when your migration happens, you first have a primary store, which is DB1 in this case. And when you write to a shadow, you create a shadow and attach the shadow to the specific namespace. And it's now writing to both DB1 and DB2. We backfill the data using forklifting, or backfill the data from DB1 to DB2. We move the DB2 as a primary, and we decommission DB1. That's how we migrate the data from one data store to another data store. All this while client is unaware of what is happening underneath the data stores. There are a lot of building blocks we built for key value store. Chunking, compression, caching, SLO, signaling, summarization, dictionary compression, adaptive pagination that we talked about earlier, nearline caching. Some of these are building blocks makes key value tunable. Ultimately, what we are building is abstraction with many tunable features. That's all I have for you today. Thank you, and feel free to add any questions you have. What is the maximum size of chunk we should send to the bucket each time? Specific bucket is 1 to 8 chunks, and each chunk is 64 KB in size. So that's your limit, right? Like maximum 1 MB of data is what we are storing. If there are more than one key which gets assigned to the same bucket, you will have more data, but 1 MB is a good way to think about it. Some hands-on with things you spoke about. Do you have any suggestions on what tech stacks to use? Yeah, for sure. You can. Netflix uses Java, and underneath the data store, it's Cassandra. So if you want to use Java as an abstraction layer and Cassandra as your data store, this works perfectly. The DDLs I was showing you was a Cassandra data store specific.
All right. Thank you, Vidya. That is all the time we have for this session. Thanks, everyone. We'll see you in the next session.